Hello students, this is SDsir again from the Temple of Excellence, that is Vidhyaashram Pre-University College. My dear students, in my session today, which is the last session from the chapter Fields and Charges, my discussion will be 2 5-mark derivations, extremely important, based on the applications of Gauss Law. I told Gauss Law and its applications thoroughly important. So today we will be doing 5 markers, 2 derivations, which frequently appear in your annual examination. Just to recall 2 important concepts from the previous session. One was the definition of electric flux. My dear friends, in today's concept, I will be using this expression quite frequently. What was the expression for flux? If you recall, we had written flux phi equals E cos theta into ds. So mathematically, electric flux ಗೆ ಏನು expression ಬರೆದ್ವಿ? Phi is equal to E cos theta into ds. E cos theta ಏನಾಗಿತ್ತು? It was electric intensity acting along the normal. ds ಏನಾಗಿತ್ತು? Area of the surface element. Then we studied Gauss law. What did Gauss law state? Electric flux across any closed surface in vacuum is always 1 divided by epsilon naught times the total charges enclosed by that surface. Therefore, from Gauss law we wrote electric flux across a closed surface is 1 by epsilon naught times q. And finally we told, if you have to apply Gauss law, there has to be a closed surface, and that closed surface was called a Gaussian surface. Now, we start understanding the first application of Gauss law. So what do I do in the first application? You can see I have written electric field or electric intensity due to infinitely long charged uniform straight wire. Andre using Gauss law, applying Gauss law, I have to calculate electric field or intensity at a point due to infinitely long uniformly charged straight wire. Nodi, shape of the conductor is given straight wire. What is the nature of the wire? Infinitely long, uniformly charged. One infinite long straight wire and consider ಮಾಡಿ, uniform charge distribution consider ಮಾಡಿ, we will calculate the electric field due to that. So, my first application of Gauss law is with respect to an infinitely long straight conductor carrying uniform charges. Now, to begin with, I will consider uniformly charged straight wire, exactly like this, a uniformly charged straight wire. Now there may be an ambiguity. First session ಅಲ್ಲಿ ಸರ್ ಹೇಳಿದ್ರು charges don't reside inside the conductor ಅಂತ. But here the charge distribution appears to happen inside the conductor. No, don't get confused. It is the two-dimensional view, which still means charges are present only on the outer surface. ಇದು two-dimensional ಆಗಿರೋದ್ರಿಂದ ಕಂಡಕ್ಟರ್ ಒಳಗಡೆ ಚಾರ್ಜ್ ಇದೆ ಅಂತಲ್ಲ. Still, charges are present only on the surface of that conductor. So, I have considered a straight wire, a straight conductor which is uniformly charged. Now, how do I believe it is of infinite length? ಇಲ್ಲಿ ಹೇಳಿದ್ದಾರೆ infinitely long ಅಂತ. If you observe the charge distribution, I have extended the distribution of charges on either sides of the wire. This extension shows that it is infinitely long. ಎರಡು ಎಂಡ್ಗಳಲ್ಲಿ ಚಾರ್ಜಸ್ನ ಎಕ್ಸ್ಟೆಂಡ್ ಮಾಡಿದ್ದೀನಿ. I have shown extension of charges, which clearly means it is infinitely long. So understand, I have considered a straight wire, uniformly charged, and it is infinitely long. Now, O denotes the center of the wire, not the geometrical center. Dipole ಅಲ್ಲಿ ಓದಿದ್ವಿ ಎಕ್ಸಾಕ್ಟ್ ಸೆಂಟರ್ ನ geometrical center ಅಂತ. This is not the geometrical center. Why? Because the wire is of infinite length. So this is not the geometrical center. O just represents the center of the wire. Now what do? I will consider a point P at a distance r from the center as shown in the diagram. I have considered a point P. P is a point which is at a distance r from the center. And what is the characteristic of P? I am calculating the electric field or intensity at this point P. My dear students, P is some point which is at a distance r from the center. And what is happening at that point P? ಏನ್ ಮಾಡ್ತಿದ್ದೀನಿ P ನಲ್ಲಿ? Electric field strength, electric intensity na calculate ಮಾಡ್ತಿದ್ದೀನಿ. So, which is the center of the wire? O. Where am I calculating intensity? Point P. What is its distance from the center? R. And as I told, electric field, this is very, very important. electric field E acts radially to the surface. E acts radially passing through the point P. So my initial considerations are simple. Just to summarize, what is the nature of the conductor? Straight wire, uniformly charged, infinitely long. So straight wire, infinitely long, uniformly charged. Which is the center of the wire? O. Where am I calculating the field? At the point P. What is its distance from the conductor? R. Nature of the electric field? Radial to the surface or radial to the point P. Now, my dear students, where do I calculate electric field? At the point P. How do I calculate? I have to apply Gauss law. So to apply Gauss law, what do I require? Closed surface. What was that closed surface called? Gaussian surface. So here I am drawing an imaginary closed surface passing through that point P. And what is the shape of the surface? Cylinder. Imaginary cylindrical Gaussian surface. Gaussian surface illa andre ನಾವು Gauss law ನ ಅಪ್ಲೈ ಮಾಡ್ಲಿಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ಅದಕ್ಕೆ ಏನು ಮಾಡಿದ್ದೀನಿ? Imaginary Gaussian cylinder, a cylindrical surface which is passing through this point P. So I have drawn an imaginary cylindrical surface which is passing through this point P. Now, the first mathematical step of the derivation, where I have to compute the electric flux. There is a bit of a practical ambiguity here. ನೀವು ಅಬ್ಸರ್ವ್ ಮಾಡಿ, ಇದೆರಡು cylindrical surfaces, ಇದೆರಡು open ends. I repeat, there are two cylindrical surfaces and two open ends. Where do I calculate the electric flux? Do I calculate it at the open ends, or do I calculate it at the cylindrical surface? ಅದಕ್ಕೆ ಏನು ಮಾಡೋಣ? We will recall the definition of electric flux, where I told electric flux phi is E cos theta into ds. ನೀವು ಇದನ್ನ ಬೈ ಹಾರ್ಟ್ ಮಾಡಿ ಇರಲೇಬೇಕು. E cos theta into ds. ಗಮನಿಸಿ ಇಲ್ಲಿ, if the electric field was perpendicular to the open ends, andre if the electric field was acting perpendicular to this normal, gamansi, if E electric field was perpendicular to the normal, then theta would have been 90 degrees. Yavaga? Only when I consider electric field is perpendicular to the normal. Andre, it is acting along the open faces. theta is 90 degrees. What is cos 90? Very clearly you know, cos 90 becomes equal to 0, which means flux becomes 0. So if electric field was perpendicular to this open faces, very clearly the flux turns out to be 0. Why? Because theta is 90 degrees and cos 90 is 0. Now, what if the field is along this normal? A cylindrical part normal act madidre, then very clearly there is no angle between E and N, which means theta is 0. But cos 0 is 1. So there is a defined flux where at this cylindrical part. Which means where do we calculate electric flux? It has to be along the cylindrical part. Why? Here electric field acts along the normal. Since field is acting along the normal, theta is 0. So some amount of flux has to be calculated. So this is the way we try to know where we calculate the flux. So where am I doing it here? Electric flux across the cylindrical part. So electric flux across the cylindrical part. Anywhere we go by the definition of electric flux, phi equals summation E cos theta ds. Ellaadru sari cylindrical part idiyalla, across that electric flux is calculated as phi equals summation E cos theta into ds. Where was electric field acting? Very clearly I told, electric field is along the normal. Torsadnalla. E is radial to the surface. Andre, it is acting along the normal. So when it acts along the normal, no angle between E and N, theta is 0. So cos theta or cos 0 equals 1. So what is happening? Electric field is along the normal, acting along the normal. So what should happen to theta? Theta should become 0, which means cos theta is 1. So in this expression, if cos theta is 1, the expression reduces to phi equals summation E into ds. Cos theta enaitu 1. Why? Because E is along the normal. So since E is along the normal, phi equals summation E into ds. Illu gamanisi neevu. Please to follow here. E is taken outside the summation symbol. When I take out anything outside the summation, what does that mean? It means that quantity has to be a constant. Since E is taken outside the summation symbol, it essentially means it is a constant. Why electric field strength should be constant? Simple reason, uniformly charged conductor. Since charge distribution is uniform, electric field strength at any point should be uniform. Therefore, E is taken out. So phi equals E summation ds. Strength of the electric field is constant. Now, what is this summation ds? Area of the surface element, which is the Gaussian surface here, cylinder. So, summation ds should be 2 pi RL. And what was 2 pi RL? It is the lateral surface area of the cylinder. Mat puna repeat martini. Generally, summation ds yen kodutte? Area of the surface element considered, which is the Gaussian surface here, imaginary cylinder ant helide. So area of the cylinder 2 pi RL. L is the length of the cylinder, which we call lateral surface area of the cylinder. Therefore, substituting here, flux equals E summation ds is 2 pi RL, and this is the flux across the cylindrical part, and I call that equation 1. So just to summarize how to calculate flux, we knew phi is summation E cos theta ds. Where was E acting? Along the normal. So what was theta? 0. So what was cos 0? 1. Phi is E summation ds. Summation ds is 2 pi RL, which was the lateral surface area of the cylinder. And therefore, phi equals E 2 pi RL, the flux across the cylindrical part. Now moving on, in order to apply Gauss theorem, I have calculated the electric flux, but need I require the total charges? Yes. How will I calculate the total charge? If you see the diagram, it is infinite length, infinite distribution of charges. So what do? I go back to one of my definitions. Straight conductor. What is the nature of distribution? Linear distribution. So linear density, we have already studied. So what is lambda equal to? Linear density, total charge divided by total length. So lambda equals Q divided by L, or Q equals lambda into L. In lambda ne yatike consider madidini? Surface density madilla, volume density madilla. Why only linear density? Because my given conductor is a straight wire. Linear distribution of charges. So I know linear density is total charge by total length. So charge is lambda into L. Now my task is simple. I have calculated electric flux in equation 1. I have calculated the total charge distribution, lambda into L. Finally, I use Gauss law. I know Gauss law is phi equals 1 by epsilon naught times total charges enclosed. Phi equals 1 by epsilon naught times, what was total charges I calculated? Lambda into L, and I call this equation 2. Can I equate equations 1 and 2? Yes. Equation 1 was phi equals E into 2 pi RL. Left hand side and come and see. Idu flux. This is also phi. So I can equate both of them. So what do I get? Right hand side of equation 1. E 2 pi RL. Right hand side of equation 2. 1 by epsilon naught lambda into L. I am comparing equations 1 and 2. So on simplification, if you observe, L and L gets cancelled. So vector E equals 1 numerator allide divided by e 2 pi na denominator tartini 2 pi epsilon naught. What remains here? Lambda, again R n cap, and this is the expression for electric intensity due to a charged uniform long wire. So E equals 1 by 2 pi epsilon naught lambda, R coming to the denominator, lambda by R n cap. To express this expression in vector form, and what was this n cap? Unit vector acting along the normal. So this is the expression for electric intensity due to a charged uniformly long straight wire. Now, as a second application, we will calculate the electric field due to an infinite charge plane sheet. And this goes as an assignment to you all, as we have done the previous derivation. The same way, I want you all to do the derivation for a plane sheet. The last application, but the most important one, my dear students, commonly asked 5 marker in the exam. Electric field due to uniformly charged spherical shell. Spherical shell, a commonly asked derivation using Gauss law to derive an expression for electric field in the case of a spherical shell, a uniformly charged sphere. That is what I mean as spherical shell. And here I calculate electric field considering 3 cases. Which are those 3 cases? In the first case, I will consider the point of consideration is outside the spherical shell. Second case, I consider the point on the spherical shell. And the third case, I consider the point is inside the spherical shell. And with reference to these 3 cases, I will calculate electric field. Now, the first case, I am considering that the given point is outside the spherical shell. Now, follow clearly. So, this is the spherical shell which I have considered. A sphere with center O. Again, there is a spherical shell, a sphere with center O. Again, not the geometrical center. Please to understand, now I say plus Q are the charges distributed uniformly on the surface. Dear students, nowhere I am using the term infinite here. Why? Sphere, uniform surface, spherical shell. So charge distribution should also be uniform. Therefore, I have considered plus Q are the charges distributed uniformly. So ಏನನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ದೀನಿ? ಒಂದು ಸ್ಪೆರಿಕಲ್ ಶೆಲ್ ಅನ್ನು ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ದೀನಿ. Charges are distributed uniformly over the shell, and O is the center of the spherical shell. As I've considered the first case, where should be my point? Outside the spherical shell. So I've considered a point P outside this shell, which is at a distance small r from the center. So what is the distance of the point P from the center? Small r. Be very careful. Small r is the distance of the point from the center. Again, where am I calculating the field? At this point P. What should be the nature of the electric field? Again, acting radial along the normal. So what are my considerations? What is the nature of the conductor? Spherical shell. Uniform surface or non-uniform surface? Naturally, uniform surface. So uniform distribution of charges. Where am I calculating the field now? At the point P, which is outside the shell. Very important. What is its distance from the conductor? R from the center. And again, electric field is acting along the normal. Now again, how do I apply or calculate electric field? By applying Gauss law. So what do I need? Gaussian surface. So again, I will draw an imaginary Gaussian surface. Here, it is not cylindrical. I'm highlighting this specifically. I wanted you all to know it is spherical Gaussian surface. Why spherical now? The given conductor is a sphere. So what is the nature of the Gaussian surface? Imaginary spherical Gaussian surface, not cylindrical. Now, again as we did, the mathematical steps remain the same. Electric flux across the imaginary Gaussian surface, whatever may be the nature of the surface, flux phi is calculated as summation E cos theta into ds. The same way, electric field is along the normal, radial. Electric field is acting along the normal. So theta is 0, cos 0 is 1. So theta is summation ds. Again, uniform distribution of charges. Electric field is constant. Take it outside. Now what is summation ds? The only change is, since I have considered a sphere now, spherical Gaussian surface, what is the area of a sphere? 4 pi r square, small r, because the distance between P and O was small r. And the area of a sphere is 4 pi r square. So summation ds is 4 pi r square, and therefore flux across the Gaussian surface is E 4 pi r square. Simple, as we did earlier. Across the Gaussian surface, flux phi is E cos theta ds. Again, E acts along the normal. So theta has to be 0. Cos 0 is 1. So you can see flux phi becomes equal to E summation ds. What was summation ds here? 4 pi r square. Why 4 pi r square? Area of a sphere, which is the Gaussian surface. Now, do I need to calculate charges here? No need. I have told plus Q. Why plus Q? It is nothing but uniform distribution of charges. So again from Gauss law, phi equals 1 by epsilon naught total charges. Phi equals 1 by epsilon naught. Now total charges is directly Q because no infinite distribution, finite distribution Q. So I've calculated flux, I've calculated from Gauss law. So again I compare 1 and 2 because left hand side is flux, right hand side E 4 pi r square equals 1 by epsilon naught Q. Simplify, E equals 1 by 4 pi epsilon naught Q by r square. Simple. Again here, uniform distribution of charges. Spherical surface alva. Illi infinite length anno concept baralla. So directly total number of charges in a Q ant barde. So 1 by epsilon naught Q. When I compare and equate electric intensity at a point outside the spherical shell is 1 by 4 pi epsilon naught Q by r square n cap. Now I want you all to highlight this result. Did I calculate intensity anywhere in this form? Yes, due to a point charge. Andre, if I consider a spherical shell with uniform distribution of charges, very beautifully, the entire system behaves as a point charge, single point charge. Therefore, I get the same result as I did there. Now, moving forward, in my case 2, I have to consider the point P is on the surface of this shell. This spherical shell itto, there was uniform distribution of charges. Point P is on the shell itself. Again the same electric field. This was the point O, R, and this distance we called capital R. Now observe, dear friends, if the point P is treated or considered to be on the spherical shell, on the surface of the shell, then this distance small r should be equal to distance capital R. Why? Simple. The point P is on the shell itself. Now there is distribution of charges, spherical surface, on the surface. So I'll consider surface density. What was the definition of surface density? Sigma is Q divided by A. Total charge by total area. Or Q now becomes sigma into A. Gamsi, small r becomes equal to capital R. Why? Because the point P is on this surface. So since now on this surface, I am considering distribution of charges, surface density, total charge by total area, Q divided by A, or Q equals sigma into A. What was A? Total area of this sphere, 4 pi r square. ಇಲ್ಲಿ capital R ಬರಿಬೇಕಾಗಿತ್ತಲ್ವಾ? But capital R is nothing but small r. So I have retained. So Q is sigma, A is 4 pi r square. What is now therefore E equal to? 1 by 4 pi epsilon naught Q by R square. But what is Q? Sigma 4 pi R square. This 4 pi gets cancelled. R square gets cancelled. So on this surface, E is sigma divided by epsilon naught. Again follow here. Whenever you are considering on this surface, field is with respect to the distribution of charges. Therefore, sigma is coming into picture. ನೀವು ಸರ್ಫೇಸ್ ಮೇಲೆ ಎಲ್ಲೇ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿದ್ರೆ that depends upon the distribution of charges. So we get sigma, which is called surface density, and again n cap is the unit vector along the normal. And finally, if I consider the point inside the spherical shell, we know inside a conductor there cannot be charges. Charges are absent. So electric field is zero inside the spherical shell. So I have calculated electric field at a point outside the shell, considering a point on the surface and inside the shell using Gauss law. So my dear students, with this discussion, I end this chapter. Hope all of you have understood, thoroughly revised this chapter. Again, as I told, it is a total weightage of 9 marks. We will again meet up in the next session with a new chapter, electric potential and capacitance. Until then, stay safe. Thank you.